Strength experiment with cashew and other nut candy brittles. A kitchen table engineering experiment. William Hovey Smith, 2020.
This is Hovey Smith, the Backyard Sportsman. And today we're going to investigate the structural properties of sugar-bonded materials. Basically, variations on peanut brittle. Now, peanut brittle is a common candy and it's been around for an awful long time. At any rate, it is well known as being a hard, sugar-based candy containing peanuts that tastes good. Yep. What is less well known is its ability to be a load-bearing structure. In short, we're going to see if we can make peanut brittle into an engineering structural material. It uses the same sort of concept as concrete.
This experiment is designed to see if the addition of soft aggregates, nuts, increases or decreases the strength of the material.
And so we're going to investigate that. The first thing we're going to do is, for our control, we're going to make a batch of peanut brittle, and we have the ingredients right here, except we're going to use cashews because that's the nuts I happen to have that have about the same properties as peanuts so far as their structural strength is concerned. The recipe for peanut brittle we're going to use is basically 1 cup sugar, 1 cup nuts, a half a cup of Karo syrup, salt, a little vanilla extract, and at the end, surprisingly, some baking soda. The baking soda does some interesting structural things, and we'll get around to that when we do it. So now, let's get some stuff on the stove, and we'll start making a nut brittle. We have a good-sized, deep-walled, heavy-bottomed pot. And to that, we're going to add 1 cup sugar, and 1/4 cup of water. And 1/2 cup of corn syrup. And we are going to start to apply some gentle heat here as we stir until things start to dissolve. We are adding our cup of cashews, and we stir. So now we have a pad of butter that we're going to add. And things are floating around in here pretty nicely. Okay, we're going to turn up the heat now. And the idea is to get this to approximately 300 degrees. So this is the early stage. You'll see it thickening later. You can see we're just getting started here. Just to check, we're not to 200 degrees yet. And we need to get to 3. I've added the salt and the vanilla, and you can see the bubbling as the excess water is boiling off. As the water is evaporating, the syrup is becoming obviously thicker, and you can feel it as you stir it. And after the water is gone, the temperatures can start rising above 212 degrees. So we'll do a thermometer check now and see where we are. We're now 275, so we're getting close. And now we're going to add the bicarbonate of soda. This is causing the formation of micro bubbles as it effervesces. And we're starting to look something more like peanut brittle now. The brittle has reached 300 degrees, so now instantly it has to go into the pan. I'm afraid my attempt at filming while also making this has caused the product to scorch a little bit. So it's a little darker colored, but you can see the strings coming from the spoon. That's about as it should be, yeah. So yeah, I think we did it. Well, here is our cashew brittle, and we are going to cut it and then cut a beam so we can test its strength. And there you can see a cross section. And here is our beam that we're actually going to test. Since what we're making here is an aggregate of sorts, I'm going to use 2 cups of nuts instead of just 1. And these almonds are the toughest nut that we have so far as strength goes. So I'm going to cut these longitudinally like this, so they will go in the mix and sort of lay and stack up, while the walnuts, on the other hand, will bridge some of the gaps and also add some structural elements. So we'll see how this does. This knife, one of my own designs, is sharp on one side only. So that way you get a good straight cut through something, even when slicing something like almonds. We now have our ingredients ready. There is a product called blanched slivered almonds that you can buy at some grocery stores in the baking department, and this saves you the cutting that I just did. So we have, as before, vanilla, salt, baking soda, and a pad of butter. And we will add the sugar and the corn syrup directly into the pot, and then we'll be started.
These are some of my knife designs based on ancient knives from China and other cultures and sold by my company, Hovey's Knives of China.
Here's our little pad of butter. Salt. And our nuts. This is twice as many nuts as we did before. So those are sitting there and floating nicely, and we can say turn up the heat on this stove to about 5, and we'll shortly start getting a boil. We're now to the boiling stage, and from here on out the stirring has to be continuous. If you stop for even a second or two, the material will start to scorch on the bottom of the pan, and you'll come up with a darker and darker mixture. But this is the water boiling out of the mix. And as long as there's water in it, it'll stay at about, the boiling point, 212 degrees thereabouts. But you'll want it to get to 300 degrees to the hard crack stage when you're making your candy. Our second trial batch of material is about to go under the saw. So we'll see what it looks like. You can see it does have a much denser set of aggregate, although not as thick. So I'm going to increase the width of this a little bit. For our testing, we're going to need some support blocks. And cut those. It also cleans the sugar material off my saw blade. We've now gotten down to the final moments where we shall see which of our preparations here produce the physically stronger product. On our second iteration, we did get a hard crack product, such as you see here. Okay. So this is our sample 1 at 3.95 ounces. We're suspending it there so it has an equal amount of bearing on each of these blocks. You have our container, and it supports a container, centered. And now we're going to add some lead shot. Now you may not have lead shot, but pennies or coins or anything that can be added in increments will do, even sand. 1 teaspoon. Two. Three. Four. Five. Six. Seven. Eight. We need to get a larger holder for the shot. So it's supporting 20 teaspoons of shot plus the weight of the steel container. It has failed. So that was a bending moment there before it crunched. Okay. So it supported 53.40 ounces. At 4.2 ounces, we suspend it approximately the same way. And we resume again. 1, 2, 3, 17, 18, 19, 20, 21. I think I saw a slight bend there. 21. Okay. And 61.60 ounces. So despite being the thinner piece, our piece with the added aggregate was stronger, although it broke not quite at the center but off to one side a little bit. Yeah, I can see a bubble where it was quite thin. Okay, we're going to examine the brakes now, see what they look like. So there were two lines of breakage. One here where it was particularly thin, and it did break across the nuts. Not along the grain boundaries, but across the nuts themselves. Yes, it did. This has much more of a cellular texture. And it did break across the cashew nuts there. There's a particularly large bubble right there underneath the surface, which could be taken as a point of weakness. Remainder here is sound. Many bubbles up here near the top of the surface. The addition of the aggregate does seem to strengthen the composition. The more aggregate, the stronger physically the pieces are. There is a maxim that says in a construction, the unit is only as strong as its weakest segment. Is that indicated here? Because the strongest segment physically is actually the sugar bonded cementing material rather than the nuts themselves. Here, the cement itself is the strongest element.
And here are the tabulated test results.
Well, what were our conclusions concerning the strength of sugar bonded nut aggregate material? Well, it would appear from the experiment that was done that the addition of aggregate actually strengthened the composition of the bean that was tested. Well, was that necessarily so? The answer is no, it's not. And the reason why that experiment was inconclusive was because of uncontrolled variables. One, on the first sample with the cashew nuts, there were very many air bubbles. On the second sample, there were few. Also, on the second sample, that sample was thinner than the first. So these 2 points alone discount the experiment as being valid. Consequently, what you do to correct it. In any such experiment, you need a base. So in this would be a straight sugar syrup beam made without the addition of aggregate and without the addition of any foaming compound. That might be your base. Then you add aggregate to it with foam and without foam, and you seek to get uniform thicknesses and widths. That way you're more nearly comparing, as the saying goes, apples with apples and oranges with oranges. With the experiment as was done, there were just too many variables to control adequately. The results may be true, but at the present, they cannot be defended on the existing data. Next, we're going to look at flour bonded materials, like this pot pie, which I'm about to enjoy for supper. And this has strength, as you can see, and there are many others that do. So, look forward to that in coming days.
The idea in any engineering testing is to test only one variable at a time. In complex systems, this is not always possible. In this case, system groups are tested separately, and then the combined system is tested. Each experimental failure allows the engineer to design a better test. Successful results are almost always based on previous failures. Question: how would you design and execute a better experiment? Write it out, draw it out, and plan exactly how you would do such an experiment to produce a defendable result. One way to get a more nearly edible result would be to use a heavy steel or cast iron boiler to cook the brittles. For more information on my books, blogs, and more than 850 videos, go to www.hoviesmith.com. If interested in my knives, go to hoviesknivesofchina.com. Good hunting and good eating from the outdoors. Goodbye, and God bless.